to those who have joined now. Shall we do week 9 or do you guys want to discuss week 5 to 8?
Sir, could you just explain me that Riemann sum? I'm just a bit confused about normal P. I don't get that.
Norm P.
No, yeah, norm.
Okay.
I have some activity question now.
Doubts. Okay. Okay. We will then discuss week 9 only. We will be in week 9 boundaries and we will discuss Riemann and
And sir,
Deep.
boundary points too. I didn't quite get it. Boundary points, like what does the sir mean in of YouTube video lectures?
Boundary point like critical points.
He
Your
took some piecewise function and like he solved something, and I didn't get it. He was finding critical point. I got that, but he said something about boundary points, and he took minus 100 and 100 in that question. So I didn't get that.
mm-hmm. Okay. Okay. What else? So Deepa, is your doubt before Riemann sum or after Riemann sum or in the Riemann sum?
Sir,
After
after
Riemann. Okay. Okay, then let us do one thing. Let us start with Riemann today and we will go discuss whatever the doubts you have. And then we will come back to the boundary points, what Pratyush Yadav has asked. Is that okay, Pratyush?
Yeah, sir.
Oh, okay, let me share my screen before that. Okay. Is my screen visible?
yes, sir.
Yes, sir. It's visible.
This Riemann sum screen visible, right?
Yes, sir.
Okay. Let us start then. Or shall we wait for 2 to 3 minutes or shall we start? Like I can see only 17. So if I remove me and my host, it will be like 15, which is very less figure compared to every session, right? Are the people joining or do they know there is a session now or they just felt like this is week 9 and as of now we don't want to do this kind of thing?
It could be because of week 9, sir.
Week 9. Okay. Okay, then we start slowly. Okay, let them join and okay. So let's come back and talk about Riemann sum in detail. Okay. So what exactly this Riemann sums mean? So what is this name Riemann sums and how it is related to mathematics? When we say sums, what exactly we are trying to find? So Riemann sums are basically used or Riemann sums actually compute the area. They actually approximate the area under the curve that represents a function f of x in a given interval using rectangles. So where is my cursor? Just a second. Just a second. I'm not able to use my cursor. Okay. Okay. Why these Riemann sums are helpful is these Riemann sums actually compute or they don't give us the exact value, but they approximate the area under a curve, under some curve that represents a function f of x in any given interval using rectangles. So what we actually do is whatever the curve we have, any curve, if you have any curve like this, and in some interval, inside some interval, let us say this is a curve that represents function f of x. So in this interval AB, what we try to approximate is, we try to approximate the area under this curve. So area under this curve is this. And what this Riemann sum does is, this actually approximates this area. Now, it won't give us the exact values, but it actually approximates this area by using rectangles. So the rectangles may be of any shape, but those will be like this. So we'll take some intervals and we build some rectangles like this and somewhat like this. So this is what we do. We convert this region into different kinds of rectangles, types of rectangles, and we compute the area of each rectangle, and we add all the areas of these all rectangles, and we say the area that is formed by these rectangles is more or less equal to the area under this curve. So that is where these Riemann sums are useful for us. So, but how do we do that? So we know what it is, and there will be some set of rules that we follow to compute these things, right? How do we select these rectangles? So what is the length of each rectangle? What is the height of each rectangle? How should I choose my rectangles so that it actually approximates the best approximation will happen? Okay, for that best approximation, what we do is we actually fix some lengths to each of the rectangle and heights to each of the rectangle. So our main idea is to find the length and the height of each rectangle. So how do we choose those rectangles is the first thing. And once you choose the rectangles, the next thing is computation. For that, this partition of an interval, there comes new terms here. So this is one new term which is called partition of an interval, which will be useful for us to fix the length of the rectangle. So what should be the length of each rectangle will be given by this partition of the interval. So now what we do is, we have a whole interval AB here. So the complete interval AB, now what we do is, we choose a finite order set of points including the endpoints. That means this particular interval AB, we choose AB, as well as we choose some intermediate points, like let's say x0, x1, xn, and so on xn, which are inside this AB. So that means if I enlarge this picture, if I try to enlarge this picture, let us say this is the interval AB. This is interval AB, and including these 2 points, what we actually take is, we take few more points inside this interval, like this, and so on, like this, like this, like this, and we say this is x1, this is x2, this is x3, this is x4, x5, x6, and so on. This may be some x10, and this may be some xn minus 2, xn minus 1, and we fix the last point as xn and the first point as x0. So why we are choosing these points is because what we do is, every interval now becomes length of one particular rectangle. So this from first x0 point to x1 point is the length of the first rectangle. x1 to x2 is the length of the second rectangle. So the length will be something like, if x0 is a and this is x1, this length will be x1 minus x0. So this particular length of my rectangle will be this point minus this point. Likewise, the second rectangle has length x2 minus x1. Third is x3 minus x2. Like this. For each and every rectangle, we found the length. Length of each rectangle is, we got now. Our next thing is to find height of each rectangle. So what should be my height or the breadth? Okay. And we say these points x0, x1, if you take this as all the points as a set and form a new set like this, like x0, x1, By considering all these points, if you form a set, that particular set is called the partition of AB. So simply the partition means, even in English wording also, partition means dividing big thing into smaller things. So using these points, we actually divide this big interval AB into small intervals. Small intervals. So that is what partition of an interval is. So we actually partition this given interval into smaller intervals. Okay, any doubts till now?
Yes, sir.
Any doubt? Yeah, please.
No, sir. No doubt. We
Oh,
got it.
am I not audible?
Yes, sir.
Am I audible or am I not audible?
Audible,
You
sir.
are audible,
Audible,
sir.
sir.
Like Omkar is questioned twice. Like my voice is not coming. Okay. Yeah, Omkar, can you just log in again? Just log out and log in again. Okay, so this is about partition. Partition actually gives us the length of rectangle. Okay, now see, here are some examples. And we see, you take an interval 0 to 10. Now this 0 to 10 can be split or can be partitioned in many ways, out of which these are three possible partitions I have taken. See, this length, this 0 to 10, what I did is I have taken intermediate 4 points, and one point is 1 and 3, 7, 9. This is one partition. So I actually divided my big interval 0 to 10 into small 1, 2, 3, 4, 5. 5 small intervals. So here x0 will be 0, x1 will be 1, x2 will be 3. So this is x3, this is x4, and this is x5. So see, x5 is 10. So this particular interval is split into 5 subintervals. So where n denotes, here n denotes the number of intervals in which we divided the big partition. So that denotes the number of intervals we divided. Now you see, the length of the first rectangle will be 1 minus 0, 1. But the length of the second rectangle will be 2. So 3 minus 1, 2. Length of the third rectangle will be 7 minus 3, 4. And 9 minus 7, 2. And this is 1. So it is not always necessary that, so you might have seen many examples like each and every rectangle has equal length. So that we make because we will get best approximation of the area. So that we will study. But partition can be made, and partition, each of the length of the partition, each length of small partitions may be different, may not be unique like this. For example, this partition. So P1 is actually a partition. Similarly, P2 also. But when in the case of P2, what happens is, so even here P2 is a partition, and this particular partition has divided this big interval into 5 parts, 5 partitions, smaller partitions, 5 subintervals, which are 0 to 2, 2 to 4, 4 to 6, 6 to 8, and 8 to 10. But the only difference from P1 is, here the partition is of equal length. So what we do, how we divided is, we divided the whole length of 10. So the big interval has length 10. We divided this big interval length of 10 into small 2 length intervals of 5 subintervals. So this is one interval, this is another interval. There are 5 subintervals. Each one of them have two length of 2. So here also this is x0, x1, x2, x3, x4, x5. So x5, so n subintervals, but the length of each interval is 2 here. 2, 2, 2, 2, 2. So the length of each interval is same here. So that is the difference from partition 1 and partition 2. So this is also a partition. Even this is also a partition. So this particular partition is 0, 5, 8, 10. So this is x0, x1, x2, x3. So when you see 3, so as n is 3, this particular big interval is divided into 3 small intervals. So the first interval is 0 to 5, which has length 5. So 5 to 8, this has length 3, and 8 to 10, this has length 2. Okay. So therefore, partition of any interval can have different number of partitions. There is no unique partition for any interval. Now let us see how we compute Riemann sums. So now that we know how to make a partition, so that these all are setting for our computing Riemann sums. As I also said, this particular partition helps us to give the length of each rectangle. Now let us try to compute Riemann sum. Suppose there is a function which has domain D to codomain set of reals. So output we expect from real numbers. So there is a function, and we say this there is one interval AB inside which is a subset of this domain D. So we are only worrying now. We are actually worrying about inside the interval AB. So we are not worrying about the whole domain. Now we restricted our domain, or let's say we are only looking inside the interval AB, and we take one partition. So P is a partition set. We take one partition x0, x1 to xn. In that x0 is A, left end point, and xn is B, the right end point. So this is the setting we actually did. Okay. Now the rest of the setting, this particular setting, will give us the heights of the rectangle. So we have to select the height of rectangle also, right? In order to compute the area of rectangle, we require length and as well as height. So length times breadth or length times height will be the area of the rectangle. So in order to choose that particular length, that particular height, we choose one point, any point, xi star. I just denoted it as xi star. Any point inside the small intervals xi minus 1 comma xi. So that means, so you see this, there we have divided this AB. So this x0 is A, x0 is A, and xn is B. Now we have divided this interval AB into smaller intervals by taking points x1, x2, and so on. There might be x3, x4, and so on. Here it may be xn minus 2, xn minus 1, xn. So what we did is we have chosen some point xi star, some point. So maybe in the first interval it is x1 star. So between x0 and x1, you choose any point and denote it as x1 star. Likewise, in the second interval, x2 star. In the third interval, x3 star. In the ith interval, xi star. So you should choose in the ith interval xi star, which should be in between or inside this interval xi minus 1 comma xi. So that means inside this we have taken it closed interval. So either you can choose the left point of that particular small interval or the right end point of the small interval. So that means your x1 star can also take x0 value or x1 value. Okay, you can choose any point inside this first interval and say it as x1 star. And x2 star you choose from the second interval x1 to x2. So x2 star can be x1, or x2 star can be x2, or x2 star can be midpoint of x1 and x2, or x2 star can be any point in between this interval x1 x2. So our main idea is of choosing this particular point is we fix the height by choosing this point. So once you choose these points, so if you have n intervals, n subintervals, that means you will have n points like this. So you will have x1 star, x1, x2 star, x1 star, x2 star, and so on, xn star. So you will have n points chosen. Now what I compute is, by taking these points, I actually compute f of x1 star. So that means function value at that point. So x1 star is this, and the function value will be this, somewhere around this. Right? This is the function value. So that particular function value, I will fix it as the height of the first rectangle. So f of x1 star is the function value, and I fix f of x1 star as my height of the first rectangle. So what I do is I take the horizontal line at that point and I fix this. Now as we have discussed, the length of the first rectangle is x1 minus x0, which is called as delta xi, delta x1. So this delta x1 means x1 minus x0. So delta x2 means x2 minus x1. Delta x3 means x3 minus x2. Like this. So delta xi means xi minus 1, where I is from 1 to n. So this delta x1, delta x2, this delta xn are the lengths, and the heights are f of x1 star, f of x2 star, like this. So now in the second rectangle, so how do we choose the height of second rectangle? As we have chosen x2 star, so corresponding to that x2 star, we find the function value of x2 star. So that will be somewhat like that, like this. And we take it as the height, f of x2 star is the height, and x2 minus x1, which is delta x2, as the length. So length and height, we got the rectangle. You form the rectangle. Similarly, you do it for the third interval. So third interval, it will be delta x3 as the length, and some point which we say x3 star, and corresponding to that x3 star, there will be function value. Function value is here. So we create a rectangle here like this. And now you can see the height of this is f of x3 star, and the length of this third rectangle is delta x3. Okay, similarly you construct all the n rectangles. So the last rectangle will be inside this interval xn minus 1 to xn. So you choose an xn star. So corresponding function value, you find the function value of xn star, that will be the height of the last rectangle, and the length of the last rectangle is delta xn. So now that we have created our rectangles and we know the heights and as well as the lengths of each rectangle, so we can compute the area of each rectangle. So the area of each rectangle will be f of x1 star times delta x1, and the second rectangle is f of x2 star times delta x2. So see, this is the height multiplied by length, or the length multiplied by height, breadth. So usually we say for rectangles breadth or height. So here I am representing it as height. So f of x1 star times delta x1 is the area of the first triangle. F of x2 star times delta x2 is the area of the second triangle. So what we have to do, we have to add up all these areas of the rectangles. So you have to add all these areas. So f of x3 star times delta x3, which is the area of the third triangle. So like this, it goes till the last triangle, f of xn star times delta xn. So this particular summation is also the same summation which we, so this big representation, if you want to represent it in very short, this is how the representation is. So it is the summation of I is equals to 1 to n f of xi star times delta xi. So this actually, if you take 1, that will be the first term, and if you take the second 2, I is equals to 2, that will be the second term. So as it is a summation, so you have to add up all those things by taking all the I values. So that will be called as SP, which is called as fancily Riemann sum. Okay. Now any doubts?
No, sir.
No? Okay.
No, sir.
Now there are different types of Riemann sums. So the types come based on this xi star, choosing of the xi stars. Okay. If I choose xi star as my left hand point of each interval, then that is called left hand Riemann sum. If I choose
Sir, one question here. Basically, if we see the diagram, it's x0 to x1. It's a shape of a rectangle. If I calculate this area, then this area, after that sum it, can I do this like that?
we are doing like that only, right? What you are doing?
It's area of first rectangle.
Okay, area of the first
Then,
rectangle.
then area of 2, area of 3, and nth number. After that, we sum it. And
Sum it.
yeah, can I get like this, or after? If I do like that, or if I do like this formula SP using this, what is the difference between that?
Nothing.
Both.
See, this SP has come from that only, right? This is actually the sum of all the areas of each and every rectangle.
Okay.
So the first rectangle is this area, second rectangle is this area, third rectangle correct area, and then rectangle area is this.
Okay.
And we added all those areas. That's it. Even that formula tells you the same thing.
Okay. And another one thing is, but when I calculating the area of first rectangle, second, third, I am not consider the x1 star. But here we are considering x1 star, x2 star, x3 star. What is the benefit of it?
See, this x1 star, x2 star, x3 star actually gives us the heights of each rectangle. How are you choosing your rectangles?
Okay, basically I'm taking the height of this first rectangle height.
How? What is your height of the first rectangle?
Through y-axis, basically. If xy plane is there.
Okay, xy plane is there here also. I just didn't. Okay, this is the xy plane.
Yes. After that, we calculate the height of first rectangle.
How? Why? How are you calculating the first rectangle? So you have this curve. Okay, let me give you.
Okay.
Okay. So this is the curve. Let's say I have given you the curve like this. Something like this. Okay. And I have given you the interval, big interval A. This is A and this is B. Okay. Or else let me say this is 1 and this is something 9. Okay. Now I have partition. I also given you the partition, something like 3, 5, 7. So this is the partition I gave you. So the first rectangle, how are you choosing your first rectangle? So that is what my question.
That means here we in question y-axis is not provided.
Okay, I have given f of x is equals to maybe this graph. Okay, x cube plus x. So this is what I have given you.
We put the value of
okay, what you are putting?
A value of x is 1, and
x is
1. Then I get the value corresponding. I get the value of y.
Okay, you get the value of y. Why are you putting 1 only? Like how can you assure that the height of your first rectangle is?
If I put the value of x, I get the point y. Where is the y? Then this is the height from y to.
Okay, so you are saying this will be your rectangle.
Yes.
So my question is,
how
can you take the height of the rectangle of the first rectangle as f of 1? So this is the f of 1, right? F of 1.
Yeah. Yeah.
How are you sure that it is f of 1? So did anyone said you that you should compute Riemann sums using left hand? Why are you choosing a left hand point as your function value and height of the first rectangle?
Okay, here,
What if the question is right hand sum?
okay.
Hmm. What if-
Here, my simple thinking was here. Okay, x-axis is provided. If I plot the, if I draw the perpendicular line, suppose from this graph, if I put the value of 1, I get the y point. This is the height of this, and after that I draw the this rectangle, and we calculate it.
Correct.
This
So
is my thought here.
Yeah, correct. Whatever
Okay.
you did is correct.
Okay.
But it is only correct when
Okay.
we have asked you like you compute the Riemann sums using left hand. You compute the Riemann left hand sum.
Okay.
If we said the left hand sum, that is what I am talking about. See here, x1 star is unknown. You can choose x1 star as x0 or x1 or any point in between x0 to x1. Okay, but you are choosing your x1 star as x0 initially.
Okay.
That is what you are doing. So what you are doing is you are taking x1 star as x0, the left hand point.
Okay.
Left hand point of each rectangle. So your first rectangle height will be f of x0, right? That is what you said, right? F of 1 is your height of the first rectangle.
Yes.
So the second rectangle height will be f of 3 in your case. So how do you choose the second rectangle? Height of second rectangle?
Height of the second rectangle, I choose here. Delta xi is the x2 between x3. X2, we put the value of x2 and get the height of this, and after that I chose
You put what
value of x2.
value of x as 2.
No, here. Okay, you are asking for x3, delta x3. I put the value of x3, then I get the height, and after that I calculated.
Correct. So what you are actually doing is you are computing Riemann sums. I don't say you are not computing Riemann sums,
Okay.
but you are computing Riemann left hand sum, where this x1 star, x2 star, x3 star, all will be the left hand points of each interval. So this x1 star will be x0. This x2 star will be x1.
Okay.
So this point itself, x1 itself is my choosing point, and I construct rectangle according to that.
Okay, got it.
Okay, but in real life, or not in real life, but in problems, not every time we ask you to compute Riemann sums by taking the left hand points. Sometimes we say x1 star to be chosen as x1, x2 star to be chosen as x2, x3 star to be chosen as x3. Okay, or x1 star is midpoint of x0 and x1. Okay, if we ask you to find Riemann midpoint sum.
Yeah.
So the question is Riemann midpoint sum. So then this x1 star you should choose as the midpoint of x0 and x1.
X1, yes.
So in that case, your x1 star will be something x0 plus x1 by 2.
By 2.
So it's not x0, it's not x1. So here also your height of the first rectangle will be, if I say midpoint, then it will be 1 and 3. Midpoint will be 2.
Yes.
Okay. And the height of your first rectangle will be f of 2, not f of 1. No.
F of 2. Yes.
Okay. So that is what x1 star means. So depending upon the x1 star, that is what we are going to see. So depending upon these xi stars. So if I take left hand Riemann sum will be, if my xi star is actually the left point, which is xi1, that means xi minus 1. That means my x1 star, I will take it as x0. x2 star, I will take it as x1. Like this, xi star, I will take it as xi minus 1 point. If I take it like that, if my xi star is equal to xi minus 1, and if I compute SP, This particular SP is called as left-hand Riemann sum. Whatever the area of rectangles we compute, and if we add all the areas of the rectangles, then that is called left-hand Riemann sum, where our xi stars are chosen as the left end points of each interval, left end points of the each interval. So x1 star is chosen to be x0, x2 star is as x1, x3 star as x2, like that. Xi star between somewhere xi star as xi minus 1. So xi star in this interval, ith interval, I choose the left end point of the ith interval, which is xi minus 1. If I choose it like that, my corresponding SP, which is the Riemann sum, is called as left hand Riemann sum. If I choose my xi star as my right end point of each interval, so if my xi star is xi, that means now my x1 star first point is, I will take it as x1, x2 star as x2, x3 star as x3. So here you can see each of the interval, this x1 star I have taken as the right end point of the first interval, which is x1, and x2 star as x2, x3 star as x3, x4 star as x4, like this, xi star as xi. So if I take the right end points of each interval, then if I compute SP, that particular SP is called, whatever the value we get is called the right hand sum. And there is one more thing called midpoint sum, where our xi stars are actually the midpoints of each interval. So this x1 star is actually x0 plus x1 by 2. So that will be the midpoint, exactly the midpoint of each interval. So each of the x1 star, x2 star, x3 star, we compute the midpoints of each of the interval. And then if you compute, so what you have to do, you have to just replace, in our formula, you just have to replace, this is xi star, right? You just have to replace xi star with xi minus 1. Here you just have to replace xi star by xi. When I say midpoint Riemann sum, you just have to replace xi star as xi minus 1 plus xi divided by 2. So whatever the formula we have, you just have to replace this xi stars by some values, by some points. So if those points are left hand points, then that is called left hand Riemann sum. If those points are right hand sum, right hand points, right side points, right hand points, that is called right hand Riemann sum. If it is midpoint, so whatever xi stars we are choosing, if they are midpoints of each of the interval, that is called midpoint sum. Now there is one more thing called trapezoidal sum, where our height will not be, where we don't consider as rectangles, we actually consider trapeziums. So this is the interval, this is the curve, let us say. Okay, let us say this is the interval. Three sub intervals we have divided. So this is A, this is B. So now what we do is, we don't actually take it as a rectangle. Instead what we do is, we join this point with this point and make it as a trapezium. So this is a trapezium, and we join this point to this point, and this is one more trapezium, and this point to this point, this is another trapezium. So what we are actually doing is, this point and this point, so we take f of A or f of x0, this is f of x0, and this is f of x1, this is f of x2, this is f of x3, which is B. So what we do is, we try to compute the area of these trapeziums. So do anyone of you know what is the area of the trapezium?
Half sum of parallel sides into height.
Sum of the half into sum of the parallel sides into height. Correct.
Right. Yes, sir.
So yeah, correct. So this is, if this is A, sorry, I don't want to bring again here. So let us say this is L1, sorry, H1, and this is H2, and this is L1. Now the area of this trapezium will be half into H1 plus H2 times L1. So this will be the area. Here the trapezium sides heights are f of x naught and f of x1. For the first trapezium, this height is, the first side height is f of x naught. The second side height is, this height is f of x1. So the area of the first trapezium will be half into f of x naught plus f of x1. This will be the times the length. So the length delta xi, delta x1. So this will be the area of the first trapezium. Likewise, you compute the area of the second trapezium, third trapezium, and that will be a summation. So SP will be now summation half into f of xi minus 1 plus f of xi times delta xi. So this is the trapezoidal sum, trapezoidal Riemann sum. So there is no xi star here. There will be f of xi minus 1, f of xi divided by 2 times delta xi. So this, depending upon these xi stars, we have different types of Riemann sums. But the formula is same and everything, computation, everything is same. So actually, this particular thing changes the height of each rectangle. That's it. So not the length of each rectangle, it actually changes the height of each rectangle. As the height changes, area of each rectangle changes, and the value we are going to get will also change. So when you compute via left hand Riemann sum, you might get some value. When you compute using right hand Riemann sum, you might get some other value which are not equal, which may not be equal. But both of them, when your n tends to infinity, both of them should converge to one particular point, one particular value. That's it. So this is about Riemann sum. This is how we compute Riemann sums. Basically, we try to construct rectangles and compute the area of each rectangle and add all the areas of all the rectangles. So that will give you the Riemann sum. So this is one example, one small example, I guess. So how will be the graph of x square by?
Parabola from
Parabola passing through
0, 0.
origin. Correct. So something like this. Okay. So we are considering our interval from 0 to 4. So you don't need to worry about other outside the interval. So consider till inside the interval only. So let us say this is 4. And also partition is given to us. So 0 is one partition. So 0 is the x naught. So this will be x naught, x1, x2, x3, and x4. So we have divided our big interval into 4 sub-intervals. So this is 1, and this is 2, this is 3. Okay.
Yes.
Right. Now we will have 4 rectangles. First and foremost thing is, as partition is given to us, compute delta xi's. So delta x1 will be 1. So how do I compute it? 1 minus 0. So this is actually x naught, x1, x2, x3, and x4. So delta x1 is x1 minus x naught, which is 1 minus 0, which is 1. So similarly, you get delta x2 as 1, delta x3 as 1, and delta x4 as 1. So you can compute all these things irrespective of what the sum is. So irrespective of what we ask, like left hand or right hand or midpoint or trapezoidal, whatever it is, whatever till now I did, you have to do that. It is common for every sum. Next, it depends on the left hand or right hand. It depends on the xi stars we choose. So now we have to choose xi stars in each of the interval. So here we have 4 sub intervals. We have to choose x1 star, 4 points like this, x2 star, x3 star, x4 star. So if we choose these 4 points, we are done and dusted. Our problem is solved. For the choosing, if I say left hand Riemann sum. So if I say compute the left hand Riemann sum, so now tell me what should be my x1 star, x2 star, x3 star and x4 star.
0, 1, 2, 3.
0, 1, 2, 3.
Correct. 0, 1, 2, 3. Because we have to choose the left hand points for each of the intervals. So this is one interval. The first interval we have to choose the x1 star as the left hand point. What if I have asked like a right hand Riemann sum? Now what will be my x1 star,
1, 2, 3,
1,
4.
2, 3, 4.
1, 2, 3, 4.
x4 star? That will be 1, 2, 3, 4. Correct. Because you have to choose the right end point of each interval for right hand Riemann. So what if I ask you midpoint
0.5,
Riemann?
1.5, 2.5, 3.5.
Correct. Very good. So x1 star will be the midpoint of the first interval. So the midpoint of the first interval is 0 plus 1 by 2, which is 0.5. Similarly, x2 star will be 1.5. x3 star will be 2.5 and x4 star will be 3.5. Understood? So now this is how we choose x1 stars or x2 stars or xi stars. So depending upon the question, we choose xi stars correspondingly.
Sir,
So
I
let
had a
us,
question.
yeah.
Sir, if we weren't given how to exercise star, so isn't trapezoid like what was the 4 type of Riemann trapezoid sum?
If we haven't given you, see the thing is we will give you anyway. It should be given, or else
Yeah,
how
but
will
if it isn't given, then that should be the most appropriate one to use, right?
most appropriate one. So for better approximation, you go for trapezoidal sum.
Yeah, trapezoidal Riemann sum.
Trapezoidal Riemann sum. But as of now, you no need to worry about those things because we will provide you anyway whether you have to compute, which one you have to compute. And there
Okay, sir.
is lower Riemann sum and also upper Riemann sum, but we are not going to touch it. Okay.
Yeah, okay, sir.
Okay. So that is why I'm not even discussing the lower and upper Riemann sums here. So for trapezoidal, we don't have. For trapezoidal sum, we don't need to select these x1 stars, x2 stars, x3 stars, x4 stars. It is sufficient to have f of x0, f of x1, f of x2, f of x3, f of x4. So with this, this is how you have to find x1 stars. After finding x1 stars, you have to create, or you just create rectangles, or this is the difference. This is how the difference will be. So if I compute left hand Riemann sum, if I have to choose, I have to choose the left hand points as my heights. So therefore the height of the first rectangle will be 0. F of x1 star is 0. F of x2 star is 1 square, which is 1. So our f of x is given to be x square. Likewise, so the first rectangle, so if left hand Riemann sum, this is how the rectangles will be. So there will be a flat line, there will not be any rectangle. because the height of the first rectangle will be 0 and the second rectangle height will be this, and the rectangle will be somewhat like this. For the third rectangle it will be like this, and for the fourth rectangle it will be like this. Okay, this is the red one represents the left hand Riemann sum rectangles. So if you compute the area, there will be a huge error. So this particular region is not covered, this is not covered, this is not covered, this is also not covered. So you can directly from the diagram itself you can say, so this particular partition doesn't give us the best approximation, or there will be a huge error between the area we compute and the area under the curve x square within the interval 0 to 4. And if I see the right hand sum or the right hand Riemann sum, so I have to choose the right hand point as my height. So this is how the rectangles will be. Okay, this is how the rectangles if I compute the right hand Riemann sum. Also you can see now here also this is also not a good approximation because it takes more area into it. It gives more area than the area under the curve. So this particular black thing is actually the right hand Riemann sum. Red thing is actually the left hand Riemann sum. When you look at midpoint sum, so this, so first we have to identify the midpoints and the function value at the midpoints. This one, this one, this one, and somewhat this one. And the rectangles will be like this. This is how the rectangles form. So you can compute this area also. You can see from the diagram itself, the areas of whatever the complete values we compute by adding all the areas, the left hand Riemann sum is very much different from the value that we get from right hand Riemann sum, and that will be very much different from the midpoint Riemann sum, right? You can compute and check. So this particular left hand Riemann sum, now it will be SP will be summation. So it will be like f of x1, f of x0 times 1. Delta xi's are 1. So no need to worry about delta x's. So delta x1 plus f of x1 times delta x2 like this. So f of x0 is 0 plus f of x1 is 1 times delta x2 is 1 plus f of x3 x2 times delta x3. So f of x2 is f of 2 which is 4 times 1 plus f of x3 times delta x4. So f of x3 is 3 square, so it will be 9 times 1. So the area will be something around 13 plus 1 14 square units. So SP will be 14 square units. But when you compute right hand Riemann sum, it will be this. You can check it. It will be this 1 plus 4 plus 9 plus 16. Okay, this will be something around 20-30. So 30 square units. You will get 30 square units. But when you compute midpoint Riemann sum, it will be something around 0.25 plus, so square of this 0.5 square, 1.5 square 2.25 plus 6.25 plus 1225. Okay, so if you add this will be the SP. So this will be something like 18, 20, 21, 21 square units. So you can see the difference here itself. So by computing left hand Riemann sum, we are getting 14 square units. By computing right hand Riemann sum, we are getting 30 square units. And by computing midpoint Riemann sum, we are getting 21 square units. So you can see the difference between the computation like this. But if you actually compute the area under the curve, so this will be 0 to 4 x square dx, x cube by 3, 4, 0. That will be by 4 cube, which is 64 by 3. So this will be around 21.33 square units.
That means midpoint is quite accurate.
For this particular case, yeah, it is quite accurate.
In right hand Riemann Sum, sir, every time is greater, sir?
No. As the curve is greater like this, so that is this particular curve, you see.
Yes, sir.
So this is an increasing curve.
Yes,
And
sir.
also it has a good curve, good shape of the curve. So that's why the left hand points values will be lesser than the right hand point values. But the graph, if the graph is something like this, then you will get left hand Riemann sum has more value than the right hand Riemann sum. But if your graph is somewhere like this, midpoint will fail here. Midpoint won't give us the accurate thing.
Okay.
Okay.
But if the delta x tends to 0, then all three are almost
All three, yeah,
accurate.
all three will come closer and closer to the accurate value, 21.3. Okay. In this particular case, it happened that midpoint has given us better approximation. Midpoint.
But in exam,
Hmm?
in exam we calculate three of these things: left hand, right hand, then midpoint. Now only we follow one thing: midpoint.
No, that we will mention. Okay, that we will give you which method you have to choose. So see, the answer differs, right? If we ask you to compute right hand Riemann sum and you have computed left hand Riemann sum, you will get 14, but the right answer is 30.
Yes.
Yeah.
Okay.
But sir, in real life, there is no method. That time, what can I choose?
That is why we have studied these many cases, different types. So in your real life data, so taking left hand points, see, that is why I have given you the differences. In this curve, if the curve is smooth and increasing or decreasing, midpoints will give you the better approximations.
Yes.
Okay. And if the curve is increasing and decreasing, left hand and right hand may not give you the accurate values, not even nearer to the values. Okay. In those cases, midpoint you have to choose.
Sir, what if we subtract right hand Riemann sum from left hand Riemann sum?
What will you get, man? If you subtract 16, you will get.
Sir, will it not be the area which is left, which is green part?
No. How will that be the green part? That will be if you subtract this red rectangles from the black rectangles, you will get this area.
Okay.
So we can take like average of left hand and right hand Riemann. That will be a better approach. Yes, sir.
Average of left hand and Riemann. That means you have to create new sum.
No, sir. Basically, this type, same query. I have the same query related. If I uh, uh, averaging the left and the right, then we get the approximate result nearer to the midpoint, and then we for that time we cannot calculate the midpoint.
So
Is it
sometimes it may
applicable?
not.
Is it not
No.
applicable for everyone?
No.
Okay, sir.
See, that is what I am saying. If it is like this and we have given partitions as like this is the partition. So if you consider the midpoints, here the midpoint sum is way larger. So this is the midpoint sum. This will be the midpoint sum. So you compute the areas of these rectangles, and this will be the midpoint sum. And whatever the points you choose, either left hand Riemann sum or right hand Riemann sum you compute, those will be like this. Here the left hand Riemann sum and the right hand Riemann sum both are same. Both you will get same values. But the midpoint sum is way larger than both of the values. So that is why I say, depending upon the curve, depending upon the nature of the curve, so we will choose which one is better. So whether to compute Riemann sum, whether to approximate Riemann sums using left hand Riemann or right hand Riemann or midpoint Riemann depends on the curve, actually the function. So function will tell us which one to be chosen. Okay.
Excuse
Here
me,
to-
sir.
Yeah.
Do we ever use a general formula to compute the area?
General formula to compute?
The area.
What is general formula?
So you had written earlier the general formula of Riemann sum.
That will be true for any Riemann sum. But you have to choose your x1 star, what we say, x1 star perfectly to get the accurate result. Not accurate result, best approximate result. You have to choose your x1 star correctly. So this xi star correctly. So this xi star for each interval you should choose. So the choosing of xi star is the big thing. So how do you choose that xi star is the issue or the major thing in this Riemann sums. Okay. So this, if you know how to choose this xi star, then you can use this formula. Okay.
Sir,
But how do you choose?
sir, I have a question. Like, why do we use Riemann Sum if we could directly integrate the function with limits to get the area under the graph?
Why to use Riemann sums?
Like,
Okay.
like when to use Riemann Sum?
Correct. This is one good. Okay. Let me give you. I also explained in one of the tutorials, I guess. If you have gone through tutorials.
Yeah, a few of videos I have left to see.
Okay. So if I have given and I asked the value of I, how do you integrate this? Hello?
No idea, sir.
No idea, sir.
Okay. What if I made it complicated? E to the power 1 plus x square divided by 1 minus x square, integrate it from 0 to 1 dx. Now, अरे 1 plus x square by 1 minus x square ही नहीं पता, you are asking, you are taking e to the power of that. So for these cases, if you are in a competitive exam or not even competitive exam and you wanted to find this value, so for these cases, what we do is we actually approximate the area. No need to find the exact area. You can actually use this Riemann sum. You can actually partition this into some subintervals. So maybe 0.1, 0.2, 0.3, 0.4, 0.5, 0.6 like this till 0.9. So each of the subinterval you take some 10 intervals and you compute, you just say the graph of 1 plus x square by 1 minus x square. Somewhere it may be like somewhat, it won't be like this, but let us assume it is like this. Then you take approximations, linear, this Riemann approximations. And computing this is much easier than this, trust me. So if it is e to the power 1 plus x square by 1 minus x square, computing e to the power 1 plus 0, divided by 1 minus 0. This value is much more easier, and also the other parts also. 1 plus 0.3 square divided by 1 minus 0.3 square. So function values at these points is easier, and when you have the function values, you have the heights of each rectangles and the lengths of each rectangles, and you can approximate, best approximation can be done for this integral 0 to 1 e to the power 1 plus x square divided by 1 minus x square dx. Okay, so there these
Okay, sir.
Riemann sums are actually helpful for you. And also, yeah, when you don't know the definite integral for any function inside this, you definitely don't know, right? 1 plus x. If I have given you integral sin x or cos x or x square, something like that, you actually integrate it directly. What if the inside integral inside function you don't know how to integrate? You don't even know how to integrate. Then for finding, so luckily you are sitting in an exam and you have values like 20, 190, 200, sorry, 220, and something like 36. Okay, you have some difference, right? Some 20 to 190 and 190 to 200, 220. You can actually use Riemann sums and you will come nearer to some value. Some value maybe 36 or maybe 190, and you choose it directly. So this will not be 190 or anything. It will be less than that. Okay. So, but this is where these Riemann sums are very much helpful. If you don't know how to integrate the given function, then these Riemann sums are helpful, quite helpful. Okay.
Sir, can I say something?
Hmm.
Just like in derivative, we have formula like UV or U by V or composite function. Is there anything in integration like this?
That is where yes, we have, right, integration by parts.
Okay, that's not, I didn't do this still again, but still, that's what I'm saying. I didn't
So if
follow.
you have two different functions, like let's say e to the power x sin x dx. So e to the power x is one function and sin x is another function.
Yes.
And we consider it as two functions, and we will compute it using this formula, integral UV formula, integration by parts formula. We are yet to see that. Okay, I have that thing also.
The
So if you
integration part is not the summarized.
yeah, we have to go. I have those.
Okay, sir.
Okay. Similarly, this thing you try, take f of x is equal to x square only, but the difference is partition. I am not choosing distinct partition, or I am not giving you the partition. I am giving it as variables. I have n partition. I have divided my interval into n subintervals, where each of the interval has length 4i by n. 4i by n. So the length of the first interval will be, so where xi's are these things. Now tell me what is x1.
Zero, sir.
What is x1?
X1 is x0, 0. X1 is 4 by n.
4 by n. X2 is
2 by n. 8 by n, sorry. 4 into 2, 8 by n.
So what I said is, I have divided this interval 0 to 4 into n subintervals. I don't know what the value of n is. But each of the interval I am dividing it like this. 4 by n is my x1, 8 by n is my x2, 12 by n is my x3, and so on. This will be
N minus 1 by 2.
By n.
By n, sorry.
And the last one is 4n by n.
4.
4n by n is equal to 4.
Okay, this is how I divided my partition. Try to compute left hand Riemann sum, right hand Riemann sum, and midpoint Riemann sum. So what will be the midpoint of 0 and 4 by n? I will give you this thing also.
2 by
2 by
n.
n.
2 by n.
6 by n. Other by 18.
Like this.
Yes.
Okay. So I have given you the points. So if I say left hand Riemann sum, you should choose your first rectangle ka height as f of 0. 4
0
by n.
subscript.
So my x1 star will be 0, x2 star will be 4 by n, x3 star will be 8 by n, like this. If I said right hand, then my x1 star will be 4 by n, 8 by n, 12 by n, like this. If I say midpoint, my x1 star is 2 by n, x2 star is 6 by n, x3 star is 10 by n. So by taking this x1 stars like this, compute left hand Riemann sum, right hand Riemann sum, and midpoint Riemann sum. Okay, will you guys do that?
Okay, sir. Try.
No,
We'll
yeah, try it. Okay, at least try to compute left hand Riemann sum now. Now I'll give you some 3 or 4 minutes. So at 7:15 till 7:15 I'll give you time. Just try to compute left hand Riemann sum using this partition. Okay, there are revision sessions for quiz 2.
When, sir?
So it is scheduled on Wednesday. One is on Wednesday and one is on Friday.
Okay.
Wednesday is actually mock discussion kind of thing and doubt clarification thing. And Friday is the revision session.
Friday, which time, sir?
Friday, you can see the schedule, right? Schedule haven't come yet.
No, sir. Calendar not.
Just a second.
It is showing there.
Let me see that. So morning 7 a.m. is the revision session.
Okay. 7 to 9.
On Wednesday, sir.
On Wednesday. No. On Friday.
Friday 7 to 9. And Wednesday, sir?
Yeah, Wednesday it is not. I cannot see the schedule yet, but I will confirm it. It will be added. Okay. So okay. What is the left hand Riemann sum value? Has anyone computed quickly?
Doing, sir.
Okay. Do. So you know what to do, right? What exactly need to be done for left hand Riemann sum? I have given you everything.
Yeah, the terms first term like 4 into 4 by n plus like this, and you have to put the formula.
Yeah, put the formula. So identify x1 stars first. X1 stars, x2 stars. Identify xi stars basically. Okay, once you identify xi stars, we have given you the function also, f of x is equals to x square. Then find xi stars and then put it in SP, which is summation I is equals to 1 to n f of xi stars times delta xi. So what will be the delta xi's at least?
4 by n.
4 by n.
4 by n.
4 by n.
All delta x1, x2, delta x. This is actually equally partitioned.
Yeah, so that will be 4I by n, right?
No, why I'm asking delta, the length of
Okay,
each.
delta is 4 by n.
4 by n.
Yes, and
For all I.
for all I.
No.
And
So
del xi star is I think 4I by n, right?
xi star is actually
4I by n, where I is equal to 1 to 4.
I is equals to 1 to 4. 1 to 4 is it?
Sorry, n.
No.
Oh,
I
this
asked
is the
0 to
0 to 4. Sorry, 0 to 4.
0 to 4 or
4 into n minus 1 by n.
Yeah, 4 into n.
Okay.
So we are
Left side.
considering the
This is the
left hand
left hand limit.
Left hand.
Yes,
hand
left
limit.
hand.
So
4 into n minus 1 by n, right?
correct. So that is what we need. That is what I asked. So what will be the value? No one computed, is it?
No, so I was confused little bit for 4i, the last one.
Okay.
Delta star, no, I
What is
star,
xi
delta
star?
xi, xi star, that's right.
Xi star is
4n, 4,
4 into I minus 1 by n.
4 minus,
very good.
4 minus
So that
1
will
by
be 4
n.
into I
4
minus
into I minus 1 by n.
correct.
And
So
another
therefore,
one is 4 by n.
another one right hand Riemann sum. You are talking about right hand Riemann sum, right?
No, no. I'm saying delta x is 4 by n.
Delta xi is 4 by n. So we will replace it with 4 by n directly.
Yes.
Okay. And this is 4 times I minus 1 by n. What will be f of xi star now?
4 of n minus 1 by n whole square.
4 of 4 I minus 1 divided by n whole square.
Yes, whole square into 4 by n. This is the summation.
This will run from I is equals to
0, sorry, I
1 to n.
1
we
to
have
n.
taken I minus 1 here. So in order to, so this will always be 1 to n only. You know it here.
Yeah,
So
I
we
is
will
going to 1
convert
to
it
n.
accordingly. Okay. In order to take I is equals to 1, we convert this f of xi star as into I is equals to 1 as base case. So now we have this. So what we have now? I is equals to 1 to n 4 square, which is 16 times I minus 1 whole square into 4 divided by n cube. So this 16, 4, n cube are independent of I. You
Can
can
be
take it
taken outside.
So that will be by 64 by n cube
Yes.
into summation I is equals to 1 to n I minus 1 whole square. So what will this be? 64 by n cube into, this is something like 0 square plus 1 square plus 2 square plus and so on n minus 1 whole square. How many of you know the sum of squares?
N into n plus 1
n
into
into
2n
n
plus
plus
1
1
is
by
6.
2n plus 1 by
6.
So if the sum is, so 0
1
can
square
be,
to n square.
yeah, 1 square to n minus 1 square. It's not n square.
No. The actual formula.
Actual formula
What we
is,
told.
yeah,
What we
you
told.
told is n into
n plus 1 into 2n plus 1 by 6.
1 by 6.
If it is 1 square plus 2 square plus n square.
N square.
Yes.
So if it is still n minus 1, what we have to
Replace n with n minus 1.
Replace n with n minus 1. Very good. So 64 by n cube into n minus 1 into n into 2 times n minus 1 plus 1 divided by 6. Correct?
Yes, sir.
This n and this will get cancelled. And you can, so this will be 2n minus 1. So n minus 1 into 2n minus 1
by n square
into 64 by n square into 6. So you can simplify this also, 32, 3. So this will be the left hand Riemann sum. Correct? And if we compute right hand Riemann sum, okay, you can take it as an exercise and you can compute right hand Riemann sum, but this will be different. Not the same expression you will get, this will be different. And also you can compute the midpoint sum also. Now why we are not giving exact values for n, why we are taking n intervals and why we are not giving value to n, like let's say 5 intervals or 6 intervals. We just said n intervals and we haven't given the value of n. Why is it so?
Probably because we want, we can increase the value of n. And
yes.
So that delta x tends to 0, so that the answer will be accurate.
Yeah. So now n is in our hands now. N is a variable now. I can choose n irrespective of whether it is smaller or bigger or very huge or n tends to infinite. So I can make n very, very, very large. By making n very, very, very large, that means I am taking number of partitions to be infinite. Very, very, very big partitions. Within the small interval itself, if my n is some 1000, I am taking some 1000 subintervals. So 1000 subintervals are somewhat like this. Very, 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 very small intervals we have. The interval length will be decreasing if I increase n. So the length of each interval will decrease. So this is, I just told about 1000. What if n is more than 1000? What if n is going to infinite? Then the length of each interval will approach to 0.
Very small.
Very small.
Tends
Very,
to
very small.
0.
Yeah, tends to 0. And if I have that as my length, and if I have rectangle for each of that interval, like this very, very small rectangles, will my approximation gets better or worse?
Better.
Better.
Better, far better.
Yeah, correct. So that means if I tend this n to infinite, so think about like that. If I am tending n to infinite means I am actually making the length of each interval is 0. Very, very 0. Very, 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 very small. When I make it like that, the value that this particular Riemann sum takes will actually go closer and closer to the exact value of the area of the curve.
Means
So
the
that
better
means,
approximation.
yeah, so that means if I make this particular thing to limit n tends to infinite, if I compute the value of this 2n minus 1 into 32 divided by n square into 3, what am I actually doing? I am tending my n to infinite so that this particular value will be better and better by each n. So if I take the limit where n tends to infinite for this, it will give me the exact value, or it will give me the error is very, very, very less, which can be neglected sometimes. So this particular thing is actually the area under the curve f of x. So what will be the limit value? We know how to compute limits, right? So how do we
64 by
compute?
3.
Right. So this n square, I split it into n, and I take into each one of it, and I will get 1 minus 1 by n
2
times
minus 1 by n.
2 minus
1 by
1
n.
by n
Into 32 by 3.
into 32 by 3. So as n tends to infinite, this will go to 0, this will go
1
to
by
0,
yeah. 2
and
into
our
32
product
by
will
3.
be
64 by
1
3.
times 2 times 32 by 3, and which is 64 by 3. So the same value 64 by 3 we have seen some half an hour ago.
Integration.
Yes.
Whatever 0 to 4 x square dx is there, this will actually compute to 64 by 3 square units. Okay.
Accurate value.
Exact value. So we are approaching to exact value. So if we take only 4 subintervals, we have seen, right? If we take only 4 subintervals like this, our value is left hand Riemann sum value is something like 14 square units. If I take 5 subintervals, maybe it will be go to some 16 square units. If I take some 100 subintervals, it may go to somewhere around 20 square units or 21 square units. Like this, if I take 1000, 2000, 3000, if I take infinite number of subintervals, what if my n is becoming larger and larger? Then I will approach to exact value of my integral or the area under the curve. So that is how we take Riemann sums, we limit Riemann sums to n tends to infinite, it will give us the exact value of the area under the curve. So limiting value of Riemann sum is the exact value. That is what we say, right? Limiting value. That is what we say, right? As n tends to infinite. I just forgot the name. So yeah, that is how we
Infinite
define
limit,
our
sir.
infinite. I forget the technical name for it, but this is the idea behind this. So when we take the Riemann sum limit as it tends to infinite, limiting value of Riemann sum, it will give us the exact value of the area under the curve of any function. Okay.
For this sum, then we can directly find the integration of it. This sum, when we ask this sum, we don't have to find the Riemann sum, right? We directly use the integration between the limits and find the answer, right?
Why to use the integration?
No, if the sum is given the exam, so we will need to compute the Riemann sum for this. Can't we integrate and find it directly?
Okay, if we ask you to limit, if we ask you to find the Riemann sum and limit tends to infinite value, you are asking me to, can't we directly integrate the value?
So that we can get the answer directly. That's what
you can
maybe
do that.
that's what she's asking.
Some
that's what I'm asking.
Some smartness you can use there. That both the values will be equal. Okay, if you know the integral, you can directly take the integral.
Sir, it's only when n tends to infinity.
Yeah, when n tends to infinity. Only this particular thing will be equal to the exact value of area under the curve. Okay, but if we have given you have to take some 5 subintervals and compute the left hand Riemann sum, then it may not be equal to the exact integral value, 5 or 10 or any. If we have given you n, if we provided you the n, then you don't have choice to pick. Then your answer might vary from the exact definite integral. Okay. So let us see what norm is. Then we can combine this definite integral to this Riemann integral. So norm of P, which is basically denoted like this. So two double mods between P is actually norm of P. And we defined norm of P as max of delta xi. So here P is the partition, and how we define norm is, norm can be defined in different ways. Okay, norm can be minimum of this. So there are different kinds of norms you can define, or norm can be the first value x naught. So norm of P can be equated to x naught directly. Norm of P can be xn. Norm of P can be minimum of, delta x1 or delta xn, or norm of P can be taken as min of all the delta xi's. So you can define norm. Here we are defining norm as max of all the lengths of subintervals. So previously in the start of the lecture, we have discussed that partition can be any way, and also whatever the partition I take, length of each subinterval may not be equal also. Correct? So these are the examples we have taken in the start of the lecture also. So there are 3 partitions for this interval 0 to 10. So partition 1 can be like this: 0, 1, 3, 7, 9, 10. Partition 2 can be 0, 2, 4, 6, 8, 10. Partition 3 can be something like 0, 5, 8, 10. So these 3 are partitions of this big interval 0 to 10. And this norm of P is defined as maximum value of all the lengths of subintervals. So that means max of delta x1, delta x2 to delta xn. So we compute delta x1, delta x2 and so on to delta xn, and we take the maximum value of out of these all values. That will be the norm of P. Okay, understood?
Yes.
So for example, you take the first example.
Then the first one will be 4.
4.
Yeah. So here delta x1 is 1,
1,
delta x2 is 2,
2,
delta x3
4,
is 4,
2,
2, 1.
So we
So it
take
will be
max
4.
of 1, 2, 4 to 1. So what will the max of 1 to 4 to 1? 4. So maximum value. Okay. So I'm getting some noise.
Sir, that's mean norm of P is not minimum or maximum. That it is given by it is given in the question that it is max or min.
We defined norm as like this.
Okay.
Okay.
Got it.
Yeah. In this particular course, we defined it like this: norm of P as max of delta x's. So the maximum value of the largest subinterval. So that is what norm is. So the big subinterval. So the big subinterval in this partition P1 is 4. So norm of P1 is 4. Similarly, norm of P2 will be
2, because it's equally distributed.
Yeah, as it is of equal length, that will be like 2, 2, 2, 2. So max of 2, 2, 2 is 2. So the norm of P2 will be 2. So the largest subinterval is 2 only. What will be the norm
5.
of P3?
5.
So you compute the lengths of each of the subintervals. So this subinterval length is 5, 3, 2.
2.
So max of 5, 3, 2 will be
5.
So you can see here, depending upon the partition, our norm value changing. So the norm for different partitions will be different. So the norm of P1 is 4, norm of P2 is 2, norm of P3 is 5. Okay. So this is what norm of a partition means, norm of P means. So why this is useful is because for this. So you see, we define this definite integral as, so this is how we define our definite integral. So the definite integral from A to B, so the lower limit or the lower end point of the interval, we take it here, and the upper limit is taken here within the integral. So below and above, inside our function f of x dx. This is the denotion of definite integral. So we are integrating. So this means we are integrating f of x in the interval a b. Okay, that means we are finding the area of the curve, area under the curve f of x within the interval a b. So that particular definite integral is actually equal to limit norm p tending to 0. So when will norm p? So norm p is actually the maximum value out of all intervals, right? Delta x1, delta x2, like this. So when will this norm p, or when will the max of the largest subinterval tends to 0?
Delta x tends to 0.
Hmm?
Delta
When
x tends to
n tends to infinity.
N tends to infinity, and whenever the largest subinterval itself is tending to 0, then my norm p tends to 0. Correct?
If the length
So,
is 0?
yeah. So if my largest, so norm p is actually the largest subinterval, right?
Yes, sir.
Subinterval. So this particular largest subinterval itself goes to 0, then my norm p goes to 0.
Yes.
So the largest subinterval I have is maybe 0.0001. That is the largest subinterval I have. Then the norm p is actually 0.0001. What if my largest subinterval itself going to 0? So whatever the interval I have is actually every interval is going to 0. Then norm p will go to 0. So that means as n tends to infinite, my norm p goes to 0.
Yes.
As my n tends to infinite, my norm p will tend to 0. That means each of the subintervals will go to 0, and max of zeros will be 0, will go to 0. maximum value will also go to 0 slowly. It will not be 0, it will go to 0. So that means this particular limit is actually limit n tends to infinite. F of xi summation I is equals to n f of xi star correct delta xi. Okay, so this particular limit just above we have seen this particular limit, this is the Riemann sum, and if we let n tends to infinite, limit value n tends to infinite, then this will give us the exact value of area under the curve, and that exact value area under the curve is actually the definite integral. We define it as integral a to b f of x dx, and these two will actually be equal to limit norm p tending to 0 0 s of p. So these three values are equal, will be equal. Okay, so if you don't understand this, don't worry much about this. So it is actually the same as this. So here it is s of p, p it is given, right? This is denoting with respect to p. That is why we are letting p, norm p tends to 0. That norm p tends to 0 is nothing but n tends to infinite. That's it. As I increase my number of intervals, my length of each interval will go to 0. And as every interval goes to 0, my max of
So
every
number
interval
of
will also,
interval will go to infinity.
yeah, number of intervals will go to infinity, and length of
Yes.
each interval will go to 0, and max of each of the intervals going to 0, max of that will also go to 0. As max of that goes to 0, norm p goes to 0. So that is how it will be. So limit norm p goes to 0 s of p is same as limit n tends to infinite summation I is equals to n f of xi star delta xi. So limiting value of Riemann sum, that will be equal to the definite integral a to b f of x dx. So we read it like that, integral a to b, a from a to b f of x dx. So that is what the definite integral means.
So norm p tends to 0 and delta xi tends to 0. Norm p tends to 0 and delta xi tends to 0.
Yeah, when delta xi tends to 0, norm p tends to 0. Correct. Okay. Yeah, there is one more concept called antiderivative. Okay. What is antiderivative? So what is derivative? If we have f of x, if we differentiate this f of x with respect to x, that will be the derivative. So that means f dash of x, something like df by dx, right? So this is the derivative of this function f of x. This is f of x, and this f dash x is the derivative. Now what is antiderivative? Antiderivative is, if I have any function, so if I have this, let us say if I have this, so this is g of x now. If it is derivative of some function f of x, okay, if this f dash of x is some g of x, then integrating this g of x gives me the function f of x. Okay, if I integrate, so backtracing, that's it, derivative, antiderivative. If I integrate this, I will get this. So that means if I integrate f dash of x, I will get f of x back.
Basically, it cancels it out, right?
Yeah, it cancels it out and it gives me f of x itself. So that is how it is. if I have some f dash of x as f of x, some function f of x, if I integrate that f of x, it will give me f of x. Okay, anti-derivative, opposite of derivative, opposite of, you can treat it like opposite of derivative. Here we are actually integrating it. Okay, integration is actually opposite of derivation. Okay, treat it like that. So that is what antiderivative means. So there are many examples, right? So integral cos x dx
minus sin x.
Minus sin x. So the antiderivative of cos x is minus sin x.
Sir, it is plus sin x, sorry.
Sir, it is sin x. Minus sin x will be
It's
derivative.
plus sin x,
That's
sorry.
So sin x, because if you derivate sin x, you will get cos x.
Cos x, yes.
Correct. Even I trusted you. Okay. I haven't taught.
No, I'm thinking it's derivative.
Okay. So what is integral sin x?
Minus cos x.
Minus cos x.
Minus cos x. If you derivate minus cos x, you will get sin x.
Yes, sir.
Yes.
Okay. So the vice versa kind of thing. So anti-derivative, the name itself tells you. So you should do opposite of derivative. So there are many formulas you can remember, or we will give you if necessary. Okay, something like tan inverse of x. This is one good thing. Integral tan inverse of x.
Don't know.
Sir, derivative is
derivative.
Derivative.
Derivative integration, I don't know.
So derivative is 1 by 1 plus x square, is it?
Yes.
Yes, sir.
Yes, sir.
1 plus.
Integration has to be done using by parts.
Okay. So this is tan inverse of x.
Yeah, this will be tan inverse x.
Yeah. See, even I am very bad at formulas, remembering formulas. So remembering all these formulas are pretty much difficult.
We have to remember all this formula for the exam, like sec x, cot x, cos square x, 1 by...
No. See, you can actually derive it. What I do is, if I forget, I will derive it. Sit and derive. It may lose some time, but I will derive. So
can you please show?
Integral secant square x.
Tan x.
Tan x. So these are very easy, right? So what I will do is, I will, if you don't know secant square integral, what I will do is, this will be cos square x by sin square x.
No, 1 by cos square x.
1 by cos square x, sec square.
Yes. 1 by cos square x.
Yes, sir.
Now you see, I will take it like this. This is something like cos x, and I take sin x and sin x. Okay.
Sir, we can say directly now. Derivative of tan x is secant square x.
Directly you can do. You can prove.
That is easy, sir. Derivative of tan x, finding out derivative is easy. Sin by cos.
Correct. So yeah, you can do that. I'm not saying you cannot do that. You take cos x as p.
Okay.
Then minus sin x dx as dp.
Okay.
So dx will be dp by sin x. Okay.
Minus.
Minus. So replace dx by minus dp by sin x, and this will be 1 by p square into dp by sin x. So if cos x is p, what will be sin x? It will be root over 1 minus 1.
It becomes complicated.
Yeah.
Yes, sir.
Then we shouldn't choose cos x square as... Okay, choose cos square x as p. Then it will be 2 cos x sin x
minus
dp. This will be sin 2x. Okay. I will tell you again. Okay. right now it will waste your time, I guess. If I sit and think, I should think for some 2 or 3 minutes.
Sir, will these questions come in exam? Means, for example.
No, even though if it come, we will give you. If formula is necessary, we will give you like table kind of thing. Okay, whatever the formula is required, we will give.
Yes, the
Means
few
all the
formulas are really
questions
tough, just like
Yeah.
would
ln
be like
x.
exam oriented, like formula oriented things or word problem things.
Can you repeat?
I'm saying that will the question be based on word problems or will it be on formula based direct inputs?
That we shouldn't say, right? That we will discuss in revision session. Maybe what kind of problems you can expect from this. Okay, I cannot directly say it's like this or it's like that. Okay, but if it is a direct calculation part, or if you require some complicated integral formulas, we will give you those formulas. Okay.
So this double integration could be the second derivative.
Yeah, it's like anti-derivative.
So it's a second derivative.
It's second antiderivative. Yeah, if you take 2 times integration, you mean, right?
Double integration.
You are integrating this and again you are integrating uske upar. Yeah, that will be like, yeah, maybe the inside one will be, the outside one will be the double f double dash of x.
Double derivative.
I
mean, is there a connection with that? I mean,
you can check, right? So this is f of x and you are integrating f of x. So if you are integrating f of x, what will you get? You will get the antiderivative of f of x, which is maybe some g of x. So if I differentiate this g of x, so g dash of x will be f of x, correct? And if I differentiate again, this will be g double dash of x will be f dash of x, which will be f of x. So that will be the double differentiation. So double integral f of x dx is gx. So the same formula got worked, right? So g double dash of x is f of x. Yeah, you can say that. Yeah, and final part is integration by parts. So if you have 2 functions with you, f of x and g of x, and if you are going to integrate the product of those 2 functions, so integral f of x times g of x dx, this particular thing will be equal to f of x times integral g of x dx. So you take the function f of x outside and times integral g of x dx minus integral, now you take derivative of this first function f dash of x times whatever the integral g of x dx is there, you take it inside dx. Okay, this comes from derivative of uv. So what is the derivation of uv?
In video lectures, the formula was quite different.
Quite different, okay, but both are same, okay.
Yeah, I was gonna ask like about that formula because I didn't get that one.
See,
they took u into they took integration of u into derivative of.
Yeah, I will. Yeah. See, even that this both are same. Okay, they might have done like this. So u dash v or u v dash.
Yes, u into derivative of v.
Yeah, u v dash they have taken, I guess. Now
Yes.
you see what happens is, if you take this as v dash, then you can directly write u into v minus integral u dash v dx. Okay, this actually comes from here only. I was about to say that.
My
So
question was how to use this formula. My question was this: like, I am supposed to take the derivative of the second term in the integral and then replace it by this.
No. Consider that as a derivative. So if you have e to the power x sin x.
So am I supposed to write sin x as cos x?
Sin x. No. You shouldn't write it as cos x. Treat sin x as some v dash.
Oh, okay.
Okay, like that. Or else, if you are treating it as one function, use the above formula.
But what you have given is that is easy formula, sir.
Easy for
There is
you.
no confusion.
Okay. Once
We
if
can
I
take
derive
f of
it,
x and g of x directly.
Yeah, because like we learned that formula in 11th, right? 11th or 12th.
Yeah.
That above
So that is
formula.
why I gave you that formula. You will connect with this formula. Okay. So whatever you learned and whatever we gave, both are same.
Sir, can you please explain that bypass formula once?
I will just come to that. Just see how this came. Okay. So what is this thing? Derivative of uv dx.
uv dash plus vu dash.
Correct. So if I integrate this, this will be like uv is equals to integral uv dash plus integral u dash v dx. So you see integral from this you will get integral uv dash dx is equals to uv minus integral u dash v dx, which is the formula we gave. Integral uv dash can be written as uv minus integral u dash v. That is what you get.
Can you please show this with one example? Can you please give an example? It's not clear for me.
Okay, I will give you an example. But those who know derivatives can understand this.
Yes, this I understand, but how could I apply on a math? That's why.
Okay. I will tell that. I will tell it an example. Tell it as an example. So if you forget this formula also, so why I gave this formula is because this is what we actually study in our younger stage. But remembering this formula, sometimes we only confuse. Okay. If you don't remember the formula and if you know the derivatives formula, so uv whole dash is equals to uv dash plus vu dash. If you know this, just integrate it. That will be the formula for integration of by parts. Okay, understood? Let us take one example which actually used to solve. So integral tan inverse x dx, is it?
Yes.
Okay, let us take this one. So in order to compute or in order to use this UV rule, you should know this particular thing, isolate. You should remember this word isolate.
It's L-I-A-T, Liat rule, right? It's not Liat, right?
It is isolate only.
What does it mean, sir?
I will tell you. How come, where come you saw that liat?
Sir, in 12th, in our textbook, it was L-I-A-T.
It's a isolate.
It's isolate only.
It was actually in form that is the
Sir, in Maharashtra board, in Maharashtra state board textbook, they given like that.
I don't know. See, but okay, let's see whether it is isolate or liat. You will get to know.
Generally, L does not come first because in some problems it does not work. So generally, this is accepted.
L does not come, is it?
I'm saying L does not come first because in certain problem that creates some problems. So this is the standard notation.
Correct. So I denotes inverse trigonometric functions. Okay, I means inverse trigonometric functions. Like, for example, sine
Sir,
inverse of x, tan
it
inverse of
means
x.
inverse function after logarithmic function and algebraic function, trigonometric function, and exponential function.
Correct. So inverse trigonometry, I denotes inverse trigonometric functions. L denotes logarithmic functions.
And A is
Like,
algebraic.
yeah, log x, ln x, these things. A denotes algebraic.
T is trigonometric. E is exponential.
Algebraic means we know, right? Polynomials.
Yes,
Algebraic
sir.
polynomials like x square, x cube plus 1. These all are algebraic. T denotes trigonometric functions.
E is exponential.
Correct. Sin x, cos x, tan x. These are. E is actually the final one, exponential function. So e power x, a power x, kind of. Okay. Why I said dilate is because you have to take dilate particular
By
order.
this sequence, we have by parts integral by this sequence only.
By this sequence. So you have u and v or f and g right above. So by choosing how we choose u, which one to be chosen as u and which one to be chosen as v. So u or f to be chosen the left. So if you have inverse function and logarithmic function, so which one inverse functions are
Then
easy?
the inverse function will be u, right?
Inverse function you take it as u.
Okay.
And the next, so whatever the first function you get
The
in
kind
this
of
order,
Bodmer's rule, just like this.
yeah, like Bodmer's rule. Okay, just
So
like
why
that.
is it so?
Huh?
Why should we take it first?
See, the derivatives of this inverse trigonometric or logarithmics, algebraics, much more easier than taking derivatives of exponential functions. So exponential function derivatives will keep on repeating. So we don't want them as u dash. So
They would reduce.
They won't reduce. They will not give you a reduced form. So actually you have to differentiate your first function, right? So if you take your first function as exponential function, that will not reduce anywhere. Okay. So that is why this order will give us a reduced form and it will be easier to compute. So here we have only tan inverse of x.
Multiply by 1.
Yeah. So if you don't have, if you have only single function, you take other function as a constant one function.
So multiply by 1 and use by parts.
Yeah, use by parts. So you multiply it by 1 and 1 comes in algebraic. So 1 is an algebraic expression. Okay. Now we have inverse trigonometric function and we have algebraic function. So your u is tan inverse of x and v is 1 here. Okay. Your u is tan inverse of x and v is 1. So this is actually u. So if I taken it as uv, integral uv dx, this will be u integral v minus integral u dash integral v dx. So u integral v dx minus integral u dash integral v dx. Now just substitute u. Here u is tan inverse of x, integral 1 dx minus integral u dash. So tan inverse of, if u is tan inverse of x, u dash is 1 by 1 plus x square into integral v. So integral 1 dx. So from here we will get this integral 1 dx. If you integrate 1, we get x.
X tan inverse x.
X tan inverse x minus
x by 1 plus
x by 1 plus x square dx.
Then how do we integrate that part? X.
Now take x square as some k. Now 2x dx will be dk. Correct? So differentiate it. So if x square is k, differentiate on both sides, you will get 2x dx as dk.
If we multiply 2x and half, then it will log of 1 plus x square, right?
Then it will be
log of 1 plus
x square.
Yeah, right.
Yeah, correct. So that is where we will go. See here 2x dx, you have to take it as dk. Now this will convert as x dx as dk by 2 divided by 1 plus k. So if you take this half outside, this will be half integral 1 by 1 plus k dk. So what is the integral 1 by 1 plus k dk?
A little bit slow.
Okay.
Give some time to understand that step dk by 2.
Okay. So what we are actually doing is we are taking x square as some other random variable k. Okay.
Yes.
Okay. So now if x square is k, if you differentiate it on both sides, you will get 2x dx is equals to dk.
Okay, x dx equal to half for dk by 2.
X dx will be half dk.
Yes. And now we put that value here, x dot dx.
X dot dx, I will replace it with a half dk.
Okay.
So numerator will be dk by
1
2.
plus,
And
and
denominator
will be
will
1 plus k.
X square, I just replace it by k.
Yes.
Now this will be like half integral 1 by 1 plus k dk.
Yes.
So if 1 by x, what is the integral 1 by x dx?
Log ln x 1 plus k.
Ln x. Correct. What is the integral 1 by 1 plus x dx?
ln 1 plus x, right?
Right. So here integral 1 by 1 plus k dk will be half ln 1 plus k. So again you replace back k with x square. So this will be half ln 1 plus x square. So the whole integral x by 1 plus x square dx
and where should we write the plus c? That in the video we should mention the constant term from where we write that plus c terms.
Where we write that?
C terms plus c, that the integration there is
just
that whenever we
just outside. So it's just the constant value plus c. So final
after
answer,
completing the integration, we will add plus c.
We will add plus c. So this will be the integral of tan inverse x dx. X tan inverse x minus half ln 1 plus x square. Once you found that, if you want to guarantee whether this is the antiderivative of this function or not, you just integrate, you just differentiate this function. So if you differentiate it, you should get tan inverse of x. So if you differentiate the first term, you will get tan inverse x plus x by 1 plus x square. Right now this is uv, differentiating uv, it is uv dash plus vu dash. So this will be like this, and the second, this will be minus half into 1 by 1 plus x square into 2x. So this and this will get cancelled. It will be x by 1 plus x square, and this is also x by 1 plus x square. This and this term will get cancelled, and it will be tan inverse of x. So for our correctness, what you do is, once you found the integral value, you just differentiate it back. If you get the function, if you get the inside integral part, then you are correct. If not, then you did some mistake inside.
So c comes from here.
C is a integration constant. Okay. So the derivative of c, if you derivate the constant, it will go to 0.
0, yeah.
So we say that is an integration constant. We keep for every integral. Okay. Yeah.
Yeah. Okay.
This is about integral things and everything. Now tell me, what are the activity question doubts? Do you have any session now?
Yes, sir. We have a solve with us of stating.
Okay. Then we will wind up. Then we will discuss rest of the things tomorrow.
Sir, yesterday you can solve the activity questions also.
Yesterday.
Tomorrow, sir, sorry.
Tomorrow, yeah. I guess we will try to solve. I am not.
Yes, sir. After sir solving with us, sir.
Yeah, after solve with us, we will talk about activity.
Okay, sir. Thank you, sir.
Okay. Yeah. Thanks for joining and have a good day.
Thank you, sir.
Thank you, sir.
Yeah. Bye.